it refresh?
I think I used this.
Yeah.
Okay. Okay. And everyone knows Pauli give us Pauli is the first one to propose a neutral, lightweight particle to explain the apparent energy loss in bit decay processes. And for the history, I will also stop here. I will skip all the important particle physics experiments to demonstrate that neutrinos exist in the universe. I will focus on neutrino cosmology. Okay, let's say the number 10. Okay, assembly observations, for example, WMAP, ST, and SPT, and Planck, and large scale structure observations surveys, for example, SDSS, DESI, and the dark energy survey provide constraints on the sum of neutrino masses and their contribution to the universe energy density. And what do we have known about mass neutrinos? So neutrinos are electrically neutral, low mass, 3 flavors, and weak interaction. And they have weak interaction with other species. And also we know neutrino oscillate. And there are 2 main possible mass hierarchies. We don't know which is correct. And the first one is normal hierarchy, and the second one is inverted hierarchy. And what do we have known mass neutrinos on cosmic scales? And the Big Bang theory predicts the neutrinos will permeate in the universe. These radical neutrinos are not being directly detected. We have many indirect evidence for these mass neutrinos. And also, in the history, due to their low mass and weak interactions with other species, neutrinos were once considered to be a candidate of dark matter. But now we think not so. They are just maybe they just contribute a small portion of the dark matter. And mass neutrinos can affect the structural formation and the background evolution of the universe. And okay, let's move on to neutrino cosmology. Generally speaking, we have 2 key parameters to describe the properties of mass neutrinos on cosmic scales. And the first one is mu. Mu is the sum of it's mass sum of 3 active neutrinos. And the second one is NF. It represents it's the effective number of relativistic species. In theory, we predict the neutrino must have a positive value, and NF should be equal 3.044. This is a very accurate value. And okay, let's move on. We will focus on the neutrino mass sum. Okay, this is the standard Big Bang cosmology, and we live here. And I think everyone know we live in an accelerating phase at the late time universe. But my recent finding shows maybe we are not living accelerating phase, because we found cosmic acceleration in lambda-CDM, but in other models, for example, dynamical dark energy, dynamical dark matter, the universe is maybe not accelerating. So everything is debating. We shouldn't believe this plot too much. Okay, and to measure mass neutrinos, we mainly have 3 probes. The first one is CMB, and the second one is baryonic acoustic oscillations, and then the last one is large scale structure observations. For example, weak lensing, galaxy clustering, and many tracers. Okay, and the previous constraints missing neutrinos. Using we assume lambda CDM model plus a free neutrino mass and nu. Generally, this result assumes a positive neutrino mass. And we also work in a framework of degenerate hierarchy. It's a physical hierarchy, but it's very efficient to extract the neutrino mass and the behavior of neutrino mass on cosmic scales. Okay. Okay, in 2018, Planck gave us a TED bound and mu is 0.12 eV. And in the last year, the SDR1, based on their BO data and the CMB data, give us a very TED bound. It's 0.072 eV. And also in the last year, actually at the same time, we found we use the extra alternative background approach, angular diameter distance, and GRB. We give a tighter constraint on neutrino mass. It's this bound is the 2 sigma upper limit is 0043 EV. Okay. I think everyone can see very clearly here. This bound is in strong tension with the terrestrial experiments. Okay. And in this year, this DR2 give us a tighter bound is 0064 EV. This DR2 have a great improvement in their measurements of BO. Okay. Actually, current data prefer phenomenologically ineffective negative neutrino mass. I think it's a chaos. It's a little bit messy in this field. But the question is, first one, the neutrino mass now, and there is a strong tension between the cosmological observations and the terrestrial experiments. And the second one is maybe, and the current data actually prefer an effective negative neutrino mass. So the question is there cosmic mass neutrinos with positive masses in light of current observations at all? So a possible solutions proposed by this collaboration is the solution is in dynamical dark energy, can relax the neutrino mass bound to a safe region. And then the left-hand side is lambda CDM. Everyone can see the bounding is very tight, and in the dynamical dark energy, specifically in the CPL dark energy parameterization, and this bounding is relaxed into a safe region. But actually, it's not. This solution is not the sole solutions. There are many solutions to this tension. And how about lambda CDM? Within lambda CDM, traditional method assumes a constant neutrino mass over 4 redshifts and scales. They ignore the possible evolution details on cosmic scales. And the solution, our solution is we assume a redshift dependent MUZ, a redshift MUZ, and a scale dependent MUK, and a redshift scale dependent MUZK. Our goal is to make a neutrino mass search framework for the far future, for example, 2050. And we should acknowledge MUZ here, redshift dependent case is firstly studied in Lawrence paper in this work. but the more important scale dependence is not considered that. But I think their work is interesting for me.
I think we need to wrap up. So maybe we need to wrap up. We do not have much time.
Okay.
Maybe come to a conclusion.
Okay. Okay, sure. Okay, I give this result. Okay, and I found this okay. The most important is okay. We found 1 beyond 5 sigma, 2, 3 sigma, and 2 sigma evidences. This indicate a possible separation of neutrino mass during the evolution of the universe. We given this 4 separation mechanism for the neutrino mass, and we have this our the shortcomings of our study. Okay, the discussion. Okay, here's the discussions. Dynamic dark energy will introduce more complexity, and future high precision CMB service such as Siemens Observatory and CMB stage 4 will provide more clues of non-zero masses. And okay, your takeaways here. I'll stop here. Yes, so sorry.
Sorry to interrupt.
Okay.
We are on the clock. Yeah, I mean, this is certainly very interesting. Unfortunately,
okay.
So in the interest of time, I would say let's talk to Deng during the coffee break to dive into details of the dependent masses. So
yeah.
So let's thank again.